said, I'm not going to go on this over and over again. I have other examples of bad correlations too. The important thing I want you to get out of this is that correlation does not prove causation. You guys are all going to go and look at the infographic on this, right? Where I said there's a difference in good science and bad science. If you have bad methods, you'll get bad data. If your equipment's not hooked up properly, we are faster than light neutrinos. Well, sorry, you'll get something like that. Move really fast. Oh, we have faster than light neutrinos. No, your equipment was hooked up wrong. If you don't wash your microbes before you extract the DNA, you'll find arsenic on your DNA. And you'll say, oh, the arsenic must be in the DNA normally. This is a special animal that has arsenic in their DNA. In fact, where I said the bloggers right away went after her, they're like, that's like not cleaning the mud off your shoes when you walk in the lab and saying you've discovered footprints. Yeah, that was an actual statement that was made. But talking smack didn't matter. It wasn't until somebody went to Lake Mono, same lake, cultured the same microbes. What she said, not happening. All right, there are examples. So the head of the experiment who claimed faster than light neutrinos, he lost his job when it turned out it was a loose cable, and he went screaming to the press, right? Actually, after that, the whole team lost their job. So we use the best evidence possible. These people thought they had evidence, but the problem with their evidence is the science was not performed properly. All right, so I said that everything is based on evidence, but you have to use good methodology. And I also said that it's the best evidence we have right now. The right now is important, like really, really important. All right. Suppose we have evidence that something happens. Well, this is what's happening. And then someone else comes up with other evidence, like, well, we used to think that. In science, this is something people have a problem. This is something that non-science people have a problem with. Scientists will firmly defend this. This is the way it is. We're sure of it. But we're not 100% sure. We'll never say we're 100% certain. We can say, I'm very, very certain. I totally believe this. But there's always the chance someone comes up with other data. If someone does, we'll abandon that idea and go with the new data. So it's not like this person wrote this and that makes it the way it is. This person got published in the British Medical Journal and therefore it is. No. Everything is open to revision and to change based on new evidence. All right, I talked about this earlier. I said that we say, oh, everything is subject to peer review, but there is a problem that doesn't always happen. What we want is this. We want other scientists to say, hey, you're making a mistake. Like I said, it's fine to talk about, but we want them to come with evidence too, right? But at least people are giving feedback. Okay, the only way we can correct errors is if other people see errors in the methodology. Hey, you need to wash those microbes first. And then if they duplicate the experiment without your mistake and they show that what you're saying didn't work. But if Rosie had made a claim that everybody already believed, if someone had said, oh yeah, we discovered the DNA has phosphorus in it, everybody would be like, yeah. Nobody would have checked that. They're like, yeah, everyone knows that. That's a problem that we have in science. We know this. It's when you have something that is different than people expect, that's when your results get checked. Does that make sense? It's not the way it should be. In a perfect world with lots of money, everything would get checked. But we don't have that kind of money. So unfortunately, peer review is not as thorough as we'd like. And I'd rather own up to that instead of saying, the great science that always works. There are things fall through the cracks, and the reason why is because we don't have money to check everything. That's sad. The other thing is, when we talk about the peer review, what other people say, he was commenting about the Rosie Redfield study, the NASA study about the arsenic in the DNA. And some people are saying, but it got published in a peer-reviewed journal. What went wrong? And this was his response. I think it was really good. He said, peer review should not be considered a thumbs up, thumbs down process like you're suggesting here. So it was in the middle of a conversation on his blog. And it should not be considered a one-time event. It should be considered a continuous process, a sliding scale. Some things that get through the normal peer review process for papers, that means they're going to get published. end up being retracted. And he's right, there's a whole website now named Retraction Watch. It's fun to look at. Insights. Results can be evaluated before, during, and after the review for a publication. Scientists do this all the time on Ready, at conferences, in hallways, in lab meetings, on the phone, on Skype, on Twitter, at ArchiveX, in the shower, in classes, in letters, and so on. It's actually a disservice to science to anoint peer review as applied at some journals into something it's not. So we talked about how to do bad science. You're all going to look at the infographic on bad science. Let's talk about how to do good science. You got to be skeptical. If results seem awesome, amazing, faster than light, life but not like we know it with arsenic, check yourself. Right? Check your equipment, go talk to another scientist, see if they can find problems. That's a lot better than running to the press, I have found, and then it turns out you don't even know how to use your own equipment and you lose your job because of it. All right, so be skeptical. And the key thing in science, if I believe this, I don't try to prove it true. If I believe this, I try to punch holes in it. And if I can't, then we have evidence I might be right. If I can, well, I need to abandon it and find something else. You revise your idea then. And it's a continuous process. Remember, the two things I was harping on here. It's a process and it's evidence-based. Process, evidence-based. You guys are down with that, right? So we try to prove things false that we think are true. Here is the scientific method. The example I like to use here is water skiing. How many people here know how to water ski already? All right, JP, when you learned to water ski, when I learned to water ski, they yelled a bunch of things back at me. You might have heard the same things. Did you ever have anybody yelling, no, lean back, no, knees bent, chair position, arms up, eyes up, look at the horizon, arms got to be straight, you can't have a bend. You've heard all those things, right? Now, if you water ski a lot, do you actually have to do any of those things?
Not really.
Exactly, you don't have to do any of them. And about the time your feet start to plane, then it matters. Then you do want your legs straight, your feet parallel, because otherwise you'll do the splits and it's very painful. But up until that point, it doesn't matter. You can lay how you want, do what you want. You don't have to look at the horizon. That's to get you to not fall over. Once you know how to ski, you can look wherever you want. Look at your friends on shore. Oh, look at me! Photo op, all that jazz. Same thing. Scientific method is like training wheels for how to think about science. I already told you the key. It's that it's a process. You go through this, you make your initial observation, but as long as you think about this idea, you're going to keep going around testing, making new hypotheses, testing. What's another way to test that? Testing. Or you do the test and it doesn't come out the way you thought it would. Just go back and you rework the idea, you keep going. It's a process that you keep going, you keep going, you keep going. And it's a simple process. When a middle schooler does a science fair, they write down, well, my hypothesis is, that's not the way you actually do it. The way you actually do most science, well, let's get our result. It's not what I expected. What? What could cause that? That could cause it. Well, that's true. That's what's causing it. It would also mean that, let's test that. That's the whole scientific method right there. You go through it in 20 seconds in your head or less. We write it up this way formally, but nobody does it like middle school where you write it up at every step as you go usually. It's usually a lightning fast thing that happens in your head. Same way that you don't go through all those steps when you water ski. All right. So what are we actually talking about with the scientific method? You look at something, you come up with a prediction, and then you test it. That's the process. That's the process. I want you to know it's a process called the control group. A control group lets you remove environmental variables from the experiment. Here's an example from a textbook. Like, oh, we're going to do an experiment. We're going to see if this chemical that's from the factory, if this chemical is killing the fish in the river. There's a lot of dead fish. So you set up 4 identical tanks, which are identical, have the same water conditions, same pH, same KH, same total carbonate hardness, same nitrates, same nitrites, same water level, same temperature, same oxygen level. Set them all up the same. This one you don't do anything to, but you put some fish in it. That's our control. And this one you put a little bit of the chemical and you see how the fish do. And this one you put a little more of the chemical and you see how the fish do. And the fourth one you put a little more chemical and see how the fish do. Then we got a really high mortality rate. All the fish are kicking the bucket. They're dying. All right. The less chemical you have, the fewer that are dying. And in the control group, they're all just swimming around happy. In that case, you would say, hey, this chemical might be killing the fish. But what would you do if instead you had some dead fish in the control group?
It might just be the fish. Like the
Yeah,
fish.
could have been the fish. It could be you don't know how to keep fish and you have bad water conditions. They may all be the same conditions, but your conditions may be rubbish. You know what? That fish needs warmer water than that. Fish needs a lower pH than that. You're just killing fish. That's why we have the control group. It would be wrong to claim that chemical X from this factory is doing something when our fish are dying for other reasons. The control group lets us say, look, the environmental variables, we know those are not what are killing fish. Understand the purpose of a control group, it lets you isolate the environmental effects from the one you're testing. And we might as well do this right now. We'll do it in a second. The thing that you are testing, the one that you are fiddling with, or I should say that I am fiddling with because I am the scientist, that's a mnemonic device for you. We call it the independent variable. That's what the I is for. The independent variable is the one that we're messing with. Our actual results of the experiment, those are called the dependent variable because the results depend on what you do in the experiment. Are you down with that? Okay. So, hey, we already said that like a bunch of times. Would you agree science is a process?
Yeah.
It's based on observations and evidence, right? Mm-hmm. Hey, you've heard it. Would you agree that when we're doing science, we actually have to have our claims, our hypotheses be testable? One of the things you need to do when you're doing science is look and see what is already known. Peer-reviewed, you read what other people have said in this area, and the reason you want to do that, the best short explanation I've heard is, it's fine to talk about thinking out of the box, but it helps to know enough about the subject to know what the box is. You need to know what other people think about the subject before you just go running off. So you would agree peer review, that means that other people have read it, other people know what's going on, that your peers agree that the experiment was correctly designed, that you interpreted your results right. That weeds out bad research. Science depends on having a hypothesis, a good hypothesis. It's in red. Testable, falsifiable. It has to be something that can be proven false. If you can't prove it false, it's not science. If you can't test it, it's not science. They need to be making predictions. If this is true, then we should see that. Good? Clear? Sounds silly. But you can't test whether it's true or false because there's no way to test it. That's not science. It's fun, but it's not science. All right. The thing I want to emphasize here is that in science we never say something is proven. We never say we have proof. We say we have evidence. Sounds like I'm splitting hairs there, but I'm not. I already told you that in science we say, this is what I believe, until someone else brings evidence, right? You heard that, right? Okay, so we never say it's proven. We say we have evidence. Because if someone else comes up with other evidence, you change what you say. The standard quote here is the famous quote from Al, no amount of experimentation can ever prove me right. A single experiment can prove me wrong. Right? Okay, you already know that there's an experimental group and a control group, right? I already gave you an example. The control is the one where you don't alter the independent variable. You don't add the chemical to the tank that causes the mutations and the not making a head and all that. You don't add the chemical that kills the fish. Are you with me? Right? Okay. The control group should have all of the same conditions. We call those standard conditions. except the one we're testing, the independent variable. The independent variable is the one that we manipulate, and we're looking for results, the dependent variable. Okay. I want you to know the word placebo. If you're doing human trials, harder than fish. So if your control group doesn't like, hey, well, we have an experimental group we give this new medicine to, and we have a control group we give nothing to. That's not going to work because the people know, hey, you're not giving me anything. So what do? You give them a sugar pill, a fake pill, doesn't have anything in it. That's your placebo. Hey, I already said you need to know an independent variable and a dependent variable. I said the independent variable is the one we're changing. The dependent variable is the results. Are you done? All right, science should be based on evidence. You've only heard it like 10 times. It's only been in red like 5. What does that tell you?
Maybe it's on the test.
Maybe it's on the test. Very good, right, John?
Not sure.
All right, not sure. I might have to add it a few more times. Hey, we can never be 100% certain in science, but we get more and more confident if we keep repeating the experiment and get the same results. If other people keep repeating the experiment and getting the same results. If that happens again and again over time, we become very, very confident. Do we agree? But doesn't mean we're 100% certain. All right, we're going to talk a little teeny bit about mathy things right now. Basically, I want you to know why sample size is important. If you have been watching, last year we had political elections. If you watched the elections, you saw a lot of really annoying people on the news. Well, the latest poll shows that candidate X is 2 points ahead of candidate Y, blah, blah, blah. And they pull up the graphic, and it says margin of error 3%. So if we say this person's ahead by 2, they could be actually 5 points ahead or 1 point behind, right? It means that they know nothing. Okay, that's what it means. There's no proof. A lot of people don't understand that. Look at these 2 experiments. This little thing is called a confidence interval. It's like a margin of error. It's a slightly different test, but same idea. We look at these 2 tests. We've got an experimental group and a control group. And wow, it looks like there's a difference. We've got an experimental group and a control group. They've got this experiment, they have the same averages for the experimental group. They have the same averages for the control group. But this test is meaningful, and this test doesn't matter at all. The reason why is because we have a very high confidence interval here, big confidence interval. That doesn't mean we're very confident. Unfortunately, it's a weirdly named test. It means the opposite. What it means is, well, this is the average we're reporting, but the true measurement for this population could be as low as here or as high as here. The true measurement for this population could be as low as here or as high as here. It's possible that things are the exact opposite of the way they look when you look at our averages, where the control group is higher and the experimental group is lower. Do you agree? That's why I said that one means nothing, showed nothing. This one, even at the lowest, even at the highest, there would be a difference between the 2, a significant difference. This is a statistically significant test. What's the difference? Lots and lots of trials, lots of subjects. The bigger the study, the more people, the more organisms, the more trials, the more you do it, the more confident we are that our number is what we measured. If you have a very small experiment, that doesn't mean anything a lot of times. Usually bigger experiments have smaller confidence intervals. I'm going to be very blunt and very clear. There's a picture like that on a test. Understand. Understand what that means. Could I be more clear?
No.
Nope. All right. So science is a process. You heard that before. The results that we want are what we call statistically significant. Like I said, the one over here is statistically significant. This one is not. What I mean is that if you could get those same results from dumb luck, from chance, they mean nothing. If you say, well, there's no way that we could get this just random luck, that means it's statistically significant. How do you know that? Well, we have specific math tests to tell us. Now, if I was to flip it 20,000 times and it was to come up tails every time, then you would believe that there was something weird going on and it was a different coin than a normal coin. Do we agree? That's what statistical significance is. Hey, this varies from a normal coin. All right, that's what we're talking about. And there are math tests that actually tell you, hey, you need X amount of trials before you have significance. That's what we're doing. Are we clear? Yep. Helped found this journal. Now, I've sort of made my biases clear about who I think are the bad guys and who are the good guys. The reason why the big mainstream journals like Science are a problem, I mean, The Lancet, Science, Nature, British Medical Journal, those are the top. There's no question. If you publish in those, you've made your name. Your school's going to want to keep you for tenure because people will come to your school just to be around you as a prof. Literally, that's okay. On the other hand, though, those results are behind a paywall. I can't read them, even with our school's access. If somebody's talking on Twitter about the latest science article, and I can't read it. I can read one that's 4 or 5 months old. The general public can't read it at all. This is kind of bad, but it's extra bad if you think about the fact that a lot of the stuff published in these paywall journals was paid for with tax money. It's an NIH study. It's funded by the National Institutes of Health. That's your money. And you don't get to read the results? Or at least don't get to read them for a year? Does that seem right to you? Well, it didn't seem right to him either. And he said, screw that, Public Library of Science, open journal. Everybody can read it. Everybody can read it at any time. Stuff's out there, it's online, just go read it. Now, because this is not as prestigious, a lot of people bag on it. They say, oh, the peer review process is not as great. That's why his thing about, hey, peer review is not as great as you think it is even at the big journal. That's what he was harping on in that quote that I gave you. Now, these are links. You can follow them. There's an argument going on in science right now about what are the right kinds of journals. You can read all about the argument right here. I want to nitpick with the book. The book says that a hypothesis, if you gather enough evidence, becomes a theory. That's almost right, but not quite. Was in everyday speech, people say, oh, I have a theory, and it means an educated guess. An explanation. Well, a scientist in that situation would not use the T word, they would use the H word. Oh, I have a hypothesis about. Okay. When we say theory, it means widely supported, and we totally believe it. Until someone comes up with new evidence that shows us wrong. What I want you to know, and it's right here, look at the logical fallacies and the 10 things people don't understand about science. These first 4 links are all useful, but especially these 2 will straighten out if what I'm saying in the PowerPoint is not clear. One hypothesis doesn't become a theory. The word theory usually is reserved for something that is widely supported, repeated tests for decades, okay, gravity, the reason I got this marker out, gravity is still considered to be a theory. Now, if I let go of this marker, what's going to happen? Don't fall. Does anybody have any question if that's going to happen? No, you're exactly right, so nobody should question it. I don't question it, it's going to fall, right? We believe gravity. We believe gravity very, very, very thoroughly because it's been tested for centuries. But it's a theory. A hypothesis may or may not have evidence. It's an explanation. But it's an explanation of this. A theory is an explanation not just of this hypothesis, of this situation, but this one, and this one, and this one, and this one. When you take this hypothesis about this situation, oh, well, that, and that, and that, and that. All the hypotheses together can become a theory if they're widely supported. Make sense? The book made it sound like there was, oh yeah, well, this one hypothesis, do it enough times, it's a theory. No. It's that a bunch of hypotheses together can let us formulate a theory. Like I said, it's a minor nitpick that I had. But are you good with that? Make sense? Okay. So it's in red, one hypothesis does not become a theory by itself, but many can be used to form a theory. A theory is something that's general, applies to many situations. So gravity is not just the attraction between a marker and the floor. It's the attraction between the moon and the sun, the moon and our oceans causing the tides. We're basing it on decades of evidence already. Then it's a theory. Good? Good? All right. Can you do science without experiments? Yeah, there's some forms of science that can be done without experiments. Astrophysicists don't have the ability to blow up a star. So there are some sciences that are based just on observation. And you can still make a test that uses observations, but they're not controlled experiments where you manipulate the variables. So observations to help us find patterns and answer questions. That was an example of a form of science that has to be done through observation. Epidemiology is another example. I believe that this strain of the virus is more virulent, more dangerous, it spreads easier than that version. Well, in a controlled experiment, you would have to take this town and unleash the virus on the two of them and see who gets sicker. We don't do that. Okay? So epidemiology is not an experimental science, it's an observational science. Wow, there are a lot of people sick over there. Hey, go over and stick some Q-tips up their nose, sterile swabs up their nose and smear them on a plate and see what's growing. Hey, do the same with this town over here. There are not as many people sick. They have similar symptoms though. Yeah, there are two different strains, and yeah, this one does spread better. That's observational science. Does that make sense? You isolate the new strain. You didn't go and experimentally, let's make these people sick. Did this, we already talked about autism and organic food sales. Just because the two move together doesn't mean they're related. Do we agree? Just because things appear to move at the same time doesn't mean one's causing the other. Here are some examples. Do you think that the Greek debt has anything to do with the number of people who use Facebook? No. Quickly. All right, so do we agree science is a process? I said this many times, right? Science is a process. Got to randomize clinical trials. Suppose that you test a new drug, but your control group is all people who are under 25, and your experimental group is all people who are over 30. Is that a good study? No, because the effects of a drug could be different on people based on their age, right? So you need to mix it up. You need to randomize your groups. Does that make sense? If you really want to do it right, you do what's called a double-blind experiment. You randomize who's in what groups. And one person does that. And then you have another person who doesn't know who's in what group record the data. And then they get together and you unblind the data. You say, okay, now show me your results for this person, and then you put it with the group they're in. And then you finally look at things. A double-blind experiment where where the person assigning people doesn't know who's going to get the treatment, and the other person who's collecting the data doesn't know who got the treatment. That's why it's double-blind. In that case, you don't bias it. You don't have either person bias it. Does that make sense? The problem you have is, hey, we're testing a new blood pressure drug. Well, this person's, after the drug, their results were like, it was only 5 points, but it was 5 lower. Yeah, that's showing a difference. You can see how that's a bias, right? If they don't know who is and who isn't, they have to treat everybody the same. Either decide 5 points is or 5 points isn't, whatever, but everyone gets treated the same if you're blinded to who belonged to what group. So we already did this. I already told you that this is like that infographic of good science, bad science. One of the big problems we have is that the general public reads things in the newspaper or hears things on the news about science instead of reading the journals directly. And I want you to know, this is very important. If you hear linked to, that's a fancy way of saying, hey, there was a correlation. When you see linked to or maybe linked to, that means it was a correlation. That means it doesn't prove causation. But the way it's reported in the news, everybody thinks, scientists have shown. No, scientists did not show. It was a correlational study. So, summary, in other words, a recap of things I thought were really important. Science is a process. You've heard that a few times, right? Okay. Observational studies or experiments can support or rule out a hypothesis. You've heard that, right? But they can never make us 100% certain about the hypothesis, because there's always the possibility there's other evidence. That's okay. I've been bitten. Ow, he has teeth. Ow, ow, ow.